Good morning, students. Yesterday we discussed the evaluation of integrals of the form in which the function f has no poles on the real line. And today we will discuss the integrals of the function which have poles on the real line as well as within the semicircle gamma. Here we exclude the poles on the real line by enclosing them within the semicircles of small radii, and this process is called indenting at a point. Now let us see some problems based on indenting at a point. So the first problem is to prove that the integral between the limits 0 to infinity of the function log x divided by 1 plus x square whole square is equal to minus pi by 4. Now let us consider the function f of z from here, which is log z divided by 1 plus z square whole square. Now let us consider the integral of this function over the closed contour C, which consists of the semicircle gamma, which is the upper half of the large circle z mod is equal to r, and the real axis from minus r to plus r, which is indented at point z is equal to 0 by a small semicircle gamma of radius small r. Now let us find the poles of the function f of z. The poles of the function f of z are given by 1 plus z square whole square is equal to 0. So from here we get two poles, z is equal to iota and z is equal to minus iota. Now only z is equal to iota, that is the pole of order 2 that lies within C. Now to use Cauchy residues theorem, let us find the residue at z is equal to iota. Now residue at z is equal to iota, that is given by the derivative of the function phi at z is equal to iota divided by 1 factorial, where phi is the function log z divided by z plus iota whole square. Now f of z, that is phi z upon z minus iota whole square. From here let us find the derivative of phi with respect to z by using division rule. That will become denominator whole square, denominator as it is, derivative of numerator log z's derivative, that is 1 by z, minus numerator as it is, derivative of denominator is 2 into z plus iota. Now let us put z is equal to iota here, and we get the value of derivative at z is equal to iota, which is 1 upon 4 into iota plus pi by 2. Now putting this value here, we get the value of residue at z is equal to iota. Now let us use Cauchy's residue theorem. Now the integral over C of the function f of z, that can be written as integral minus r to minus r of the function f of x plus integral over the semicircle gamma of radius small r plus integral between the limits small r to capital R of the function f of x plus integral over the semicircle gamma of the function f of z. This integral is equal to 2 pi iota into the residue at z is equal to iota. Now the residue at z is equal to iota, that is 1 upon 4 into pi by 2 plus iota. So putting the value, we get the value of this sum of the integrals. Now this can further be written as, by simplifying this term, that will become pi by 2 into iota pi by 2 minus 1. Now as z will approach to infinity. Let us find the value of z into f of z, because we will find these integrals one by one as capital R approaches to infinity. The value of this integral, that will be 0. We will show this by using the theorem number 7, which we already discussed. And in order to use that theorem, let us find the limit of z into f of z as z approaches to infinity. Now putting the value of f of z and z into f of z, this, and taking limit as z approaches to infinity, that is 0. So by theorem 7, the limit of the integral of the function f over gamma as r approaches to infinity, that is given by iota into pi minus 0 into 0, that will be 0. Now let us find the limit of z into f of z as z approaches to 0. Now z into f of z as z approaches to 0, that also becomes 0. So we can use this theorem. According to this theorem, if AB is an arc of the circle z minus a mod is equal to r, and limit z approaches to a of z minus a into f of z, that is k, then the limit of the integral of the function as z approaches to 0, that is iota into theta 2 minus theta 1 into k. So using this theorem here, the limit of integral of the function of the circle gamma, whose radius is small r, as r approaches to 0, the limit of this integral will become 0 by using this theorem. Now let us take small r approaches to 0 and capital R approaches to infinity in this equation 1, and we get the value integral minus infinity to 0 of the function plus second term becomes 0, third term will become integral 0 to infinity of the function f of x, fourth term is again 0, and this is equal to pi by 2 into iota pi by 2 minus 1. Now let us find the value of this integral by making this limit as plus infinity. So consider this term. Now let us put x is equal to minus y. So dx will become minus dy. So the limits of the integral, they will become 0 to infinity log of y into minus 1 can be written as cos pi plus iota sin pi, that will be e raised to the power iota pi dy. In the denominator we have 1 plus y square whole square. Now log m into n, that is log m plus log n. So this term will become log of y plus log of e raised to the power iota pi, that will become iota pi. So changing y into x here, this integral will become integral 0 to infinity log of x plus iota pi into 1 upon 1 plus x square whole square dx. Now let us again substitute this value in the equation 4. This equation will become integral 0 to infinity log of x plus iota pi upon 1 plus x square whole square plus integral 0 to infinity log x upon 1 plus x square whole square is equal to pi by 2 into iota pi by 2 minus 1. Now let us equate the real parts on both sides. Now equating the real parts on both sides, here the real part will be log x upon 1 plus x square whole square plus integral 0 to infinity log x upon 1 plus x square whole square. On the right side, the real part is minus pi by 2. Now these two terms are same, so this will become 2 times integral 0 to infinity log x upon 1 plus x square whole square, that is minus pi by 2. So we get the value of this integral, which is minus pi upon 4. So this was one of the examples. Now let us see one more example based on identity. Now in the next problem, we will evaluate the integral 0 to infinity of the function x raised to the power a minus 1 upon 1 minus x, and also the integral of x raised to the power a minus 1 upon 1 plus x. Here a is greater than 0 and less than 1. Now let us find the poles of the function z raised to the power a minus 1 upon 1 minus z. Now here, because a is less than 1, so 1 minus a will be positive. So the poles of the function are given by 1 minus z is equal to 0 and z raised to the power a minus 1 minus a is equal to 0. So we get two poles of the function. One is 0 and another is 1. These are the simple poles and they lies on x-axis. Now let us consider the integral of the function f over the closed contour C, which is consisting of the upper half of large circle gamma and the real axis from minus r to plus r, which is indented at 2 points. One point is z is equal to 0, another is z is equal to 1. By taking two small semicircles gamma 1 and gamma 2. Let us take the radius of this circle is r1 and radius of this circle is r2. Now there are no poles lying within C. So by Cauchy's theorem, integral of the function over C, that will be 0. So we get integral. Now C consists of the following parts. One is this semicircle gamma, another is this line, then this semicircle gamma 1, then this line, then this semicircle gamma 2, then this line. So we have the sum of these following integrals is equal to 0. Integral over the semicircle gamma of the function f plus minus r to r1 of the function f of x plus integral of the function f over gamma 1 plus integral of the function f between the limits r1 to 1 minus r2 plus integral over the semicircle gamma 2 of the function f of z plus integral of f of x between the limits 1 plus r2 to r is equal to 0. Now as capital R approaches to infinity and small r1 and r2 approaches to 0, we will have to find the limits of these integrals. The limit of this integral as capital R approaches to infinity, the limit of this integral as r1 approaches to 0, limit of this integral as r2 approaches to 0. In order to find these limits, we will use the Theorem 6 and Theorem 7. Now let us find the value of these integrals one by one. So firstly, let us consider the integral minus infinity to 0 of f of x. Substituting the value of f of x here and putting x is equal to minus t. Dx will become minus dt. So this integral takes the form integral 0 to infinity t into minus 1 can be written as e raised to the power iota pi, and this whole raised to the power is a minus 1. In the denominator we have 1 plus t. Now let us simplify this value. So we get the value of integral between the limits minus infinity to 0 of the function f of x, which is negative of integral x raised to the power a minus 1 into e raised to the power iota a pi upon 1 plus x dx. In the same way, we can find the integral 0 to infinity of the function f of x. That will be given by integral x raised to the power a minus 1 upon 1 minus x. Now, to find the limit of the integral of function f of z over the circle gamma, semicircle gamma 1 as r1 approaches to 0. To find this limit, let us find limit z approaches to 0 of z into f of z. Putting the value of f of z here and taking limits as z approaches to 0, we see that the value is 0. So putting the value in this formula, we get limit of the integral of the function over the semicircle gamma 1. As r1 approaches to 0, this value will be 0. Now, to find the limit of integral of the function f of z over the semicircle gamma 2 as the radius r2 approaches to 0. To find this limit, we require the limit of z minus 1 into f of z as z approaches to 1. Now putting the value of f of z here and taking limits as z approaches to 1, we get the value minus 1. So putting the value in this formula, minus iota into theta 2 minus theta 1 into k2. k2 is minus 1, theta 2 is pi, theta 1 is 0. So putting the values here, we get the value of this limit, which is iota pi. Now let us add the equations 4 and equations 5. Adding the two, right side will become iota pi. Now it remains to find the limit of integral of the function over the semicircle gamma as capital R approaches to infinity. To find this limit, we require the limit of z into f of z as capital R approaches to infinity. Now putting the value of f of z here and taking limits as capital R approaches to infinity, that is 0. So putting the value in this formula, we get the value 0. So we have obtained the values of k1, k2, k3, and by using them we have obtained the limits of the integrals of the three semicircles: semicircle gamma 1 and semicircle gamma 2. Now we can put all these limits in the equation 1. So the equation 1 becomes minus integral 0 to infinity of the function x raised to the power a minus 1 into e raised to the power iota pi a upon 1 plus x plus integral 0 to infinity of the function x raised to the power a minus 1 upon 1 minus x plus iota pi is equal to 0. Now let us equate real and imaginary parts. Now from here, the real part will be minus integral 0 to infinity x raised to the power a minus 1 into cos pi a upon 1 plus x, and this is also included in the real part. So that is 0 to infinity x raised to the power a minus 1 upon 1 minus x dx. On the right side, real part is 0. Now equating the imaginary parts, imaginary part from here will be minus integral 0 to infinity x raised to the power a minus 1 into sin pi a upon 1 plus x, and from here imaginary part is pi. On the right side, imaginary part is 0. So from here we can find the value of the integral 0 to infinity x raised to the power a minus 1 upon 1 plus x, which is pi upon sin pi a. Now we can put this value here in the equation 8. So from the equation 8, integral 0 to infinity of the function x raised to the power a minus 1 upon 1 minus x, that will be pi into cot of pi a. So we have obtained the values of the two integrals, which are given by the equation 10 and the equation 11. So these were some problems based on the evaluation of integrals of the functions which have poles on the real line. And same type of more examples you can do from the book.